Okay, girls. Let's talk about the second part of the immune system. You know, yesterday we talked about innate immunity. So I'm gonna pick on like innate immunity. What does that mean? Right. So, like for example, we think about like something like the flu, right? Does everyone know where the flu originates? Actually, it originates in not humans. It doesn't originate in humans. It actually originates in birds. Yeah. So, but that's actually the exception. Most things that animals have, we are innately immune to them, which means that we can't really get them. There's only a few things that, however, those few things that we do get, you know, they're very popular in the media. So we get these things from other sources, but most of the times we don't because we have innate immunity to it. So the example up here on the slide is polio. You guys know what polio is? No? It's a virus that can cause paralysis. And I can't remember the name of the president. It's a famous American president that actually had paralysis due to polio. I can't remember his name now. My memory's really bad. But mice can't get it. Now, why can't mice get it? Because when you look at their cells, they don't have the right receptors for the virus. So if you're born with that genetic difference that prevents you from getting sick in the first place, that's innate immunity. So most things that animals get, we don't get because we are not genetically exactly the same as them. But there are things that, yeah, they can cross the species barrier, like the flu, for instance. You remember the swine flu? So where did that come from? Yeah. So, but it probably originated in birds, got into pigs, and then from pigs it went into us. Okay, well, we're going to do today we're going to talk about what's called acquired immunity. So this is the stuff where your immune system learns over time how to deal with something, okay? So this is something that will develop. All right, this is a picture of your lymphatic system, other organs involved in your immune response. So let me ask you a question. So you can see, for example, things like the appendix up here, the spleen, the thymus, lymph nodes, tonsils, adenoids. These are all part of your immune system. Where do all of these cells go? Where do they originate? Where does your immune system originate? Where do the cells come from? You don't know? I never asked you this question yesterday. Like your white blood cells, where do they come from? Right here. Bone marrow. So have you heard of a bone marrow transplant? Why would someone need a bone marrow transplant? Okay, you ever hear of leukemia? Okay, what's leukemia? Cancer of what? Cancer of your white blood cells, right? Leukemia, leukocytes. Leukocytes are white blood cells. So sometimes what happens is the person has to have their entire immune system wiped clean through radiation. Through radiation. And so what happens then is you can't live a normal life without an immune system. So you might have to get a transplant. So after your immune system's been wiped clean through radiation, you might have to find a donor to get bone marrow transplant so that you could, you could live a normal life. Because without an immune system, you're going to have to live in a bubble. And there are people actually born with a condition, it's called SCID. I can't even remember what SCID stands for, but it's SCID. And they have to live in an environment that's sterile. Because you can imagine, without an immune system, even this, the most harmless of pathogens could take you down. And that's actually what happens with someone who has uncontrolled AIDS, right? That's your immune system that's being destroyed. But we'll talk about, oh look, Facebook notifications came up. Even though we can't get into Facebook and at the school level. So, your white blood cells originate in your bone marrow. Okay, that's where they originate. You can see it here. And then what happens is they might move to different parts of your body to mature. So they start off as stem cells, and then they go this process where they mature. Now, the two types of cells that we are going to focus on in the third line of defense are the B cells on the left here, and then the T cells. And the way I remember the T cells, so they both start off in the bone marrow, okay? And then what happens is the T cells will move into what's called the thymus, which is located right above the heart, okay? And they will mature there. So think T for thymus, okay? And these are the two cells that we are going to focus on in the third line of defense. We talked about some cells yesterday that are involved in the second line of defense, like macrophages and natural killer cells, and even remember the mast cells. Those are the cells that release histamine. Today we're going to focus on the specific line of defense. And you'll see why it's called specific, whereas the other one is non-specific as we go through this, okay? All right, so we're going to talk about acquired immunity, and what you're going to see, a really important concept, is this thing called antigen presentation. Now, let's start with this word antigen. The word antigen refers to anything that, hold on a second. Okay, so the word antigen is anything that provokes your immune system. And that could be as simple as like you have an allergic reaction to peanuts. So on the peanut itself, there's something that your immune system is recognizing that's provoking it. So whatever that molecule is that your immune system sees and says this is not normal and launches an attack, that's what an antigen refers to, okay? So you'll see as we go through this, it's literally a molecule that sits on the surface of a cell that your immune system can see. Okay, so let's take a look at actually how this works. And we're going to see the role of the T cells, okay, and the B cells. So you're going to see something very similar as to what you saw with hormones, that there's going to be receptor involved, where something will recognize something else through a receptor interacting with some other molecule. Just the same way that cells can respond to hormones, the interaction of the hormone and the receptor. You see it's very, very similar when we look at the immune system. Okay, so let's take a look at basically this idea of antigen presentation. So what you're seeing in this slide right here, okay? This here is a cell in your third line, your specific line, okay? Part that learns. And you can see, so here it is, this is called a cytotoxic T cell. And here's a helper T cell. Both of these cells are involved in your third line of defense. And what you're seeing is that they're interacting with another cell. Now this cell is infected, and what it's doing is it's presenting something from the invader. Okay? And you can see the interaction right here. You can see it going on. Let me change the color so you can see this a bit better. You can see the interaction. Okay, thought I changed the color. There we go. You can see it right here. And here. So what's happening right now is the two T cells on the bottom are seeing the antigen from the invader. So let's go into that a little bit further, okay? So the 3 cells that we're going to look at are called helper T cells. And these are the ones that you'll see are, I like to think of them as like the generals. They're the ones that kind of organize the third line of defense. The other 2 cells are called cytotoxic T cells. And you're seeing that right here, okay? And then you have your B cells. And here is that general right here in the middle. This is the one that organizes the attack, okay? So you're seeing the same concept. You're seeing that presentation of an antigen. So let's basically show you the big idea here, okay? So on the left is this bacterium. So you got a cell, like a macrophage, that swallows up this invader. And what it does is it breaks it apart, and it takes the antigens, and the antigens are, again, anything that your immune system can spot and recognize, and once it recognizes it, will launch an attack. What this cell does is it takes those antigens and it pushes it to the surface of its cell. Okay, so to the cell surface. So once it pushes it outside, the helper T cell will come around and will see it. And once it sees it, it gets triggered. And you can see that the helper T cell recognizes the antigen, and then what it does is there you can see this positive means there's chemical communication. So you can see this chemical communication between the presenting cell and the helper T cell. And the positive means it's like a positive effect, not negative feedback. It's a positive feedback effect. And here's the chemical that's being released. It's called interleukin 1. And you can see that chemical stimulates the helper T cell. Once the helper T cell is stimulated, it secretes interleukin 2. So you can see that interleukin 1 has a positive effect on the release of interleukin 2, which then stimulates the 2 other cells. So in other words, if this doesn't happen, there is no immune response. Your immune system has to see that antigen for it to attack it. Now this is important, okay? This is very important because I'll tell you, in grade 11 you learned about probably the ABO blood groups. You guys learn about that? Okay. So here's the question: why is it that you can get blood type O? Why can you get blood type O? Because there's no antigen. So there are 2 types of antigens. There's A, which I'll draw as a rectangle, and then there's B, which I'll draw as a triangle, and then there's O, which is nothing. So for your immune system to launch an attack, it has to see something. The reason why you can't launch an attack against blood type O is because there's nothing there to recognize. It's invisible. Yeah. Okay, that's a different marker. So there's A, there's B, and then the plus and minus is what's called the rhesus factor, and it was discovered in a rhesus monkey, okay? So I'm going to draw that as a circle. So either you have the factor or you don't. So if you're blood type O, you have no antigen, you don't have the A or you don't have the B antigen, so you don't see that. If you're blood type O negative, you don't have the AB antigen and you also don't have the rhesus factor. So there's actually on a cell, there's many things that the immune system can see, and the AB antigen is 1 and the rhesus factor is something else. So the universal donor would be what? O negative. Because you're missing the AB antigen, you're also missing the rhesus factor. Why is what? Sorry? Because, okay, that's a good question. So remember, what we're talking about here is what your immune system is learning, right? So the third line is what you what you learn. It's not what you're born with, it's what you learn. So if you're a person and you're all, let's say you're A positive, okay? Let's say you're born A positive. What does your immune system learn over time? That A is normal and positive is normal. So what happens then is if it sees B, it learns that that's not normal and it attacks it. But if it sees O, well, it can't see O, so it can't attack. It can't attack what it can't see. So the reason why you can get O negative is because you can't see the AB antigen and you can't see the rhesus factor. So you've learned that if you're A positive, the A is normal and positive is normal. Yes, you can. Yeah, you can have A negative as a donor. Because if you're A positive, right, you've learned that A is normal, and you've learned that positive rhesus factor is normal, right? So if you get blood type A, that's normal. If you get blood type A negative, it can't see the rhesus. It can't launch an attack against that because there is no rhesus factor. There's nothing there for it to see and attack. It has to be able to see it to attack it. Okay? That's a good question. We're actually going to come back to that a little bit later on. I don't know if we'll get to it today. Okay, so the three types of cells in this line of defense are the helper T cells. Then we have the cytotoxic T cells that actually go out and kill. So to me, they're like the natural killer cells. They actually track down specific things, and you'll see why it's, again, we'll talk about why it's the specific line of defense. So these things actually track down and directly kill pathogens. And then we have, so here's actually an example of this. So here is one of these cells, and here it's launched an attack. And you can see once it launches an attack, you can see it almost looks like it's not eating it. What it's using chemicals, kind of like natural killer cells do. The chemicals literally start to destroy the membrane of the host cell, and you can see like a big chunk of the pathogen has been taken out. So the reason why it's called the specific line of defense, because this thing has specifically tracked down this type of pathogen. Whereas in the non-specific, as long as it's an invader, it will go after it. In the specific line, it will say, like, okay, imagine you have a bunch of boys coming to St. Joe's and they shouldn't be here. And you have boys from Baybuff and you have boys from Chaminade. The non-specific would be, okay, if it's a boy, let's just get rid of it. The specific line of defense would say, okay, Emily, you go after the Baybuff boys. Jerusha, you go after the Chaminade boys. It's very specific, and again, you'll see why in a few minutes. Okay, and then we have the B cells, and these are the ones that make antibodies. And I think that's summarized here. So let's take a look at actually how this works. Again, same idea, right? You have to be able to see it to attack it. So here you're seeing a cell that swallows up a bacterium, and you can see on the surface of the bacterium, you see these little markers, these antigens, okay? This gets swallowed up, the antigens get presented. Now, how does a B cell know what to attack? Well, the B cell has to be able to interact with the antigen also. Otherwise, it won't know what to go after. And so you can see on the right that a B cell that has a matching receptor for the antigen on this pathogen, you can see that they're interacting, right? So if that B cell gets stimulated, it will go after, so it will launch an attack against that type of pathogen. So what happens then is here are the antigens that are being pushed to the surface. Along comes a helper T cell. Okay, we talked about they communicate with each other, right? Through the release of interleukins. And then the helper T cell stimulates the B cell. Now, the B cells then start to divide and launch an attack. And this is called the humoral response. Okay? This is the part that produces antibodies. Everything that we're talking about is actually summarized really neatly in this chart. Okay? Everything's summarized really neatly in this chart. So you can see the idea. The idea is you have some pathogen, and on the surface of the pathogen is this antigen. Okay? Well, these antigens. The antigens get swallowed, the pathogen gets swallowed up by some cell. The antigens become presented to your immune system. So it's like the macrophage is saying, here you go, guys. This is what you're gonna have to go after. The helper T cells will recognize that and become stimulated. So they start to divide, and they send messages out to on the left the B cells, and on the right the cytotoxic T cells. Those cells will then go out and launch an attack. So the cytotoxic T cells will divide, and they will go and look for anything that has that antigen's feature. So if they're looking for an antigen that looks like a rectangle, they'll go out and look for that. And if they find it, they'll kill it. Whereas maybe a different cytotoxic T cell might be tracking down things with triangles. So maybe you have a bacterium that has this antigen and a different bacterium that has this antigen. So what happens is the cytotoxic T cells will, specifically go after one, not both. On the left, the B cells will divide, and they'll start making what are called antibodies. And those antibodies are, again, specifically geared towards either this antigen or this antigen. And they will be released by the B cells, and they will flood through your body to track down that invader. Now, I have an animation that summarizes all of this, so why don't we take a look at it, okay? Yeah. We'll talk about that. Yeah, we'll talk about that. So this is the specific line of defense.
Adrian Wilson's rhinovirus likely entered her body through her nose.
That's a continuation from
For Adrian and every other person catching a cold, infection begins when the virus particles enter cells lining the nasal cavity and reproduce themselves inside the cell. When the infected cells burst and die, they release cellular debris, including virus particles, into the surrounding tissue. Some of the virus particles in the tissues may leak into lymph vessels and travel to lymph nodes, such as the tonsils. As virus particles pass through lymph vessels and nodes, B cells are waiting for them. B cells are produced in the bone marrow and migrate into the lymphatic system.
Now you'll notice the B cells. So that's one of those three cells in your third line, right? There's three types: the B cells, the cytotoxic, and then the helper T cells. You'll notice, however, that the B cells have these receptors on the surface, and if you look closely, they are a little bit different from each other. Okay? They're a little bit different from each other. By the way, where was this B cell hiding? Yeah, so in other words, in your lymphatic system. So the cells of your third line are also called lymphocytes because they live in your lymphatic system. Okay?
If we look closely at the virus particles, we see proteins protruding upward from the surface. These proteins are called antigens because they generate an immune response. If we look closely at a B cell, we see Y-shaped antibodies anchored to its plasma membrane. Each B cell has copies of an antibody with a unique immune system provides a formidable defense against an enormous range of invaders.
In other words, an antibody is just really the receptor on the surface of a B cell. That's what it is. Okay?
When a rhinovirus antigen comes in contact with a matching antibody shape, the antibody and antigen bind together and form an antibody-antigen complex. In addition, macrophages that engulf virus particles during a non-specific immune response can present viral antigens to matching antibodies on the B cell. The binding of antigen to antibody initiates an immune response tailored specifically to this strain of rhinovirus.
Now what's missing so far? What cell's missing here? The helper cells, right? So,
although the B cell's antibodies have bound the viral antigens, the B cell still needs a little help in initiating specific resistance. That responsibility falls to helper T cells, which are also activated by viral antigens. The activated T cell binds to the antigen-bound B cell and secretes protein growth factors called interleukins. Interleukins stimulate the B cell to divide, producing hundreds of B cell clones that are identical to the initial B cell.
so there's that role of the helper T cells to get the B cells to basically divide. Because, I mean, what you want is you don't want one little measly B cell launching an attack. You want to make an army of that type of B cell. Because if that type of B cell has a matching receptor for the invader, then you want many copies of that B cell, because that's the one that will have high success in launching an attack against that specific invader. And that's what you're seeing in here.
Many of these B cells differentiate into plasma cells, which mass produce antibodies specific for the viral antigen. Once mature, each plasma cell secretes over 1,000 free-floating antibodies per second into the lymph fluid. Not all of the B cell clones differentiate into plasma cells. Some may become memory cells. Memory cells contain the same antibody as the original B cell and stand ready to produce clones. Plasma cells and thousands of antibodies send the same strain of rhinovirus into the body again.
So that's why you don't get, or you shouldn't, unless there's something wrong with your immune system, why you shouldn't get sick the second time from the same type of pathogen. Okay? So, because what you're doing is you're making these memory cells that remember the invader, so that next time you get it, it's like, oh yeah, I remember that. I'm going to launch a quick attack so you don't get sick. Unless the pathogen is different. Like, for example, the flu, there's not one flu. There's many types of flu. So unless you get the exact same flu, you're probably going to have to go through the whole process of getting sick before your immune system learns to attack it.
The lymphatic system carries thousands of newly produced antibodies into the bloodstream near the heart. From there, they are pumped through blood vessels into the body's tissues. As thousands upon thousands of antibodies flood into the tissues, they bind to antigens on the surface of the rhinoviruses. The binding of antibodies to rhinovirus proteins neutralizes the virus by causing virus particles to clump together. Scavenging macrophages home in on these antibody-virus complexes and devour, digest, and destroy them. Eventually, this tag team of antibodies and macrophages overwhelms the rhinovirus, and the infected person is able to recover.
By the way, and it's the same process if you're, for example, been poisoned. Now, you've been poisoned. The problem is this: you don't have the time to do all of this. Does anyone know how long this process takes? Like, how long does it take by the time you get like a pathogen in your body to by the time your third line recognizes it and starts launching an attack? Does anyone know how long that takes? So if you get the cold, how long does it take you to recover from that? Yeah, it's about because it takes about a week. It takes about a week for your immune system. Because think about what has to happen, right? Your immune system has to see it. And remember, where's the third line? It's sitting in your lymphatic system, right? So by the time it sees it, by the time it divides and launches an attack and clears it, it takes about a week. So if you are poisoned, do you think you can rely on your immune system to protect you? No. So you might have to take what's called antivenom. And the antivenom would be some other organism has resistance to the venom. What you're getting is you're probably getting the antibodies from that organism. Like, for example, maybe it's an antivenom from a horse, right? So the horse has these antibodies because it's resistant to the snake. You get them. How does it work? Remember, we talked about your nervous system and how venoms or poisons like TTX actually have to sit inside something. Like, remember, TTX has to sit inside the sodium gate. So how would this prevent that from working? Take a look. What is it doing? No, it's not though. The antibodies actually attach themselves to the what? To the antigen, right? So what would happen if you have a poison, a toxin that has a perfect fit for a sodium gate, but now all of a sudden the toxin is surrounded in antibodies? What can't it do anymore? It can't fit inside that sodium gate. It's kind of like, and I know I've used this analogy a million times, but it would be like if the venom is the key and the gate is the lock, and now we put tape all around the key. The tape is like the antibody. Can that key fit in the lock anymore? No, it doesn't, right? So the antibodies, not only do we make them against pathogens and living things, but your body can also generate them against things that are not living, like venom, okay, or even like pollen, for example, stuff that you breathe in. And we'll talk about that when you talk about allergic reactions.
Adrian Wilson was able to fight off the cold with the assistance of helper T-cells, the key component of specific resistance. As we saw earlier, helper T-cells secrete interleukins, which stimulate antibody-containing B-cells to proliferate, form plasma cells, and produce massive quantities of antibodies that target a specific infectious agent. Helper T-cells also activate cytotoxic T-cells, which attack and kill cells infected with viruses. One of the reasons why human immunodeficiency virus, or HIV, is such a devastating infection is that HIV is able to bind to receptors on helper T-cells and destroy the cells. Without helper T-cells and interleukins, activated B-cells cannot proliferate, form plasma cells, and produce antibodies. Such a severely impaired immune system is not able to fight off colds, as well as a host of other opportunistic infections. Without treatment, the result is usually death from pneumonia or other complications that could have been defeated by a healthy immune system.
Okay, so that's an animation that shows you kind of, how the third line, how it works. Okay, and again, that's summarized here. So what you saw in the video is the antigen presentation, right? The interaction between the helper T cells and the B cells. They didn't so much show you the cytotoxic T cells. And then what also you see in this diagram is you get the formation of what are called memory cells, so that if you do get this exact same type of pathogen a second time, your immune system response is really quick. So you're getting sick because it takes a while for this process to happen. If your immune system can respond really quickly, you don't get sick. So second exposure, which involves the memory cells, is really, really rapid response. And it's actually, you can see how rapid it is here. So this graph shows you antibody production over time. So you get an initial infection. So maybe someone sneezes and you inhale the pathogen. It depends on how the pathogen is spread, right? So you get initial exposure. About a week later, you start making antibodies. Again, why a week? Because it takes a while to present to the third line. It takes a while. What's happening during that time? The pathogen is dividing, it's spreading, you're getting sick, right? Your immune system, the second line has recognized that your second line is releasing chemicals that are giving you symptoms such as a runny nose, right? That's happening during that time. Then your third line kicks in and starts making antibodies. Now the antibodies will flood your body, latch onto the invader, neutralize it in some way, and there are different ways antibodies work, and don't worry about the different ways. I don't really care if you know the different ways they work. Just know that they neutralize the invader. Okay, so they neutralize the invader in some way. Okay, here you can see here, like for example, with a toxin, it would surround the toxin and block it. But if it was a virus, none of the viruses, same idea. A virus wants to get into the cell, so if you coat the virus in antibodies, you can't do that anymore. So what happens then is the antibodies will attack, that will clear the pathogen from your body, and antibody production goes down after the infection. Now that makes sense because you want to be able to increase antibody production when you're getting sick or when you're sick, but then at the same time you want to reverse that, right? Otherwise, what would happen? Your blood would constantly be full of what? Antibodies and white blood cells, and that's not a good thing. Your white blood cell count should go down if you're not sick, not go up. If your white blood cell count is going up and you're not sick, that's a bad sign, right? That could mean that you have leukemia or some other cancer of the blood. So this, you can see, goes down. Now take a look. If you get the exact same pathogen a second time, look at the response. It's not only is it more quick, but it's also more what? More efficient, or I don't know if you want to use the word efficient, maybe more dramatic, maybe more powerful. Just take a look at the amount of antibodies you make the first time and compare it to the amount you make second exposure. It's more. So not only is your immune system responding more quickly, it's also responding with more antibody production, so you don't get sick. If it's a different pathogen, so imagine this is flu A, make antibodies, okay, we clear it. And then we get flu B. Well, flu B and flu A do not look like each other, so your immune system has to learn again. So there's that 1 week delay before you start seeing antibody production. By the way, this is the whole idea behind vaccinations. Does anyone know what a vaccine is? Yeah, you're presenting a dead version of the pathogen. The idea is whether it's alive or dead is irrelevant. You want to show the antigens to the immune system. You want your immune system to see what it looks like. So once it sees what it looks like, and it's better if it's dead, because that way it won't do anything. But if you can show your immune system the body and what it looks like, then it will learn to attack it. And it will learn to make antibodies, and then you will form those memory cells. And if it's something like the chickenpox that's stable, you get the vaccine, your immune system attacks it, your immune system learns, makes memory cells. That way, if you do get it, your response will be really quick and you don't get sick. That's the whole idea behind vaccinations. Now, do they always work? Why not? Why don't vaccines always work? Why don't they always work? Anyone know why? So how do they make the flu vaccine? When does a vaccine come out for flu? Does anyone know? Yes, I guess you guys will get the flu shot. When does the flu vaccine come out? Before winter. When is flu season? During winter. So, what are they doing? they're making the vaccine before the flu season. So why doesn't it always work? Sorry? Right, because what they're doing is they're making it's an educated guess based on trends in other parts of the world, what the predominant types of flu you'll be getting in this area. So they make the vaccine based on those types of flus. But sometimes they're wrong. And it makes sense because you can't just snap your fingers to make a vaccine. It takes a while. It takes a few months to make the vaccine for any particular pathogen. So they have to start mass producing it beforehand, which means they got to plan. We think this is what's going to happen. If you remember the swine flu outbreak, the production of the vaccine took a few months before so that you had the swine flu outbreak initially, and then it was about a few months before that vaccine actually came out. I don't know if you remember that. That was about 7 years ago, 2009. You guys remember that? Yeah. So it takes a while for this to happen. All right. So, are you guys okay with how the third line works? Yeah. You sure? Okay. What we'll do tomorrow we'll have just a little bit left. We'll wrap it up. We'll talk about allergic reactions, which you'll see is basically, if you understand how the third line works, you should understand the allergic reaction. And then we'll wrap up with some diseases. And I will explain, we will leave off talking about how we get all of this diversity in the third line. Because here's the question I'm going to leave you with, okay? And this is the one we'll address tomorrow. How many different types of antigens are there? Yeah, there's millions. Think about all the different things that can make you sick. Each one's going to be slightly different than the other, so they're all going to have these slightly different antigens, right? So there's millions of possibilities. So that means your immune system has to figure out what is not normal and what is. And if it figures out what's not normal, it has to be able to find a B cell that can attack what's not normal. So if you have millions of possible things that are not normal, that means you have to have millions of possible B cells that can attack what's not normal. So I'm going to give you an analogy to explain this, okay? Imagine not normal is like events that you can go to. Okay? So think about events that you can go to. Funeral, school, dance, a game, right? All of these things that you could possibly go to. Working in the garden. All of these things that you can possibly go to. Would you wear the same clothes to all of those events? If you were going gardening, would you wear the same thing that if you were going to go to the prom? No. So all of these things that can make you sick, and there's all of these different types of antigens, you need to have all of these different types of B cells to attack them. Just like if all of these events that you can go to, you need to have all of these different types of outfits so you can go to them. So tomorrow we're going to address the problem, how do you get all of this variety in your immune system to be able to find B cells that can attack pretty much anything. Okay? So we'll talk about that tomorrow. All right, ladies? That is it.